Good afternoon. When I was preparing the meeting, I asked Professor Popović, is he willing to give a talk in this special seminar? And he said that he is willing to participate. He said, you know, this is such a great meeting and a good group, so he needs to participate. So here I am. Thank you, Professor Popović, for inviting me. Now, this is just to wake you up after lunch and other things, but other than that, I'll try to put you to sleep again. So we heard two talks about endoskeletons, skeletons, and everything else. And my task will be to talk about a little bit about exoskeletons and what we can do with those. And I think that's an absolutely intriguing, I would say, field of research for many, many years. It started in, I would say, 50s or 60s of last century, and there were all kinds of devices that were presented. And we can see, when we go on streets, that there are hundreds of people, individuals, walking with exoskeletons and participating in life activities, which means that this technology is really kicking in. But I think actually that the time is here where some of these devices may actually start helping individuals with special needs, and that's what I will address. The most important element in my talk is actually related to a very specific issue that Professor Marco Molinari touched. Engineering, rehabilitation engineering is a field where we should, if possible, in specific ways, assist individuals that they regain functions. Whenever we can have a better life, we'll try to have a better life. We're often talking about standing and walking, but if you just look at us at this specific moment, I'm the only one who's standing. Everyone else is sitting, which is normal. And if instead of chairs you have beds, there will be very many who will be laying down. And if there is a chance that there is someone who will be providing me a massage, you will have a massage associated with this. So in general, we want to have a happy life with a smile, and we want to enjoy the life. And that's the most important thing. And in order to do that, we found out that actually, if we just look into the normal development, children when born, they are starting to learn how to live. The very first thing, they learn smell. Then the next thing, they start learning a touch. They learn the touch by touching with their mouth. So then later on with their tongue, later on with their hands, later on with their other parts of the body, they learn how to use their eyes. And we can see that there is a constant learning procedure. And this learning procedure is actually building, like we saw today very nicely, building of synergies, building of specific connections in different parts of brains and different parts of spinal cord, having an integrated system, and all of that seems to work very well. So if there is an injury, being stroke, spinal cord, or something else which will lead to an injury, then we suddenly lose parts of the reservoir that we had. So we don't have all the cortical structures that we had before that, we don't have all the spinal cord, and we are back into our childhood. Our motor system is back to our childhood. We don't know how to operate. So in order to actually get these functions back, the best way to do is to try to relearn with now reduced potentials. Now we do not have all the resources that we had before, but we have limited resources. Most of injuries today are incomplete. Being stroke, where only part of the brain is injured, or spinal cord, where thanks to excellent first care, people are, in most cases, incomplete injuries. So the way how we can assist with this is like we're doing this when developing motor control. This is exercising, doing things, trying, and then by errors, from errors, learning and improving. We can do the same in a rehabilitation. So what we can do, we have a therapist which moves extremities to a range of movement, and that's the passive movement. We can have and ask individuals to make their maximum effort and have active movement. In the case that this doesn't work, we can potentially assist them with some type of electrical therapy, so electrical induced movement, or what I will be talking most of the day is to use robot therapy, and that is to use an external skeleton. So basically what happens is, because of the paralysis, there are a few things that will happen, and this is inactivity. Inactivity leads to dying of structures. Inactivity leads to atrophy of muscles. Inactivity leads to the decreased range of movement. Inactivity leads to depression. Inactivity is terrible. So what we have to do is we have to change from inactivity to activity. And Mark Hallett said nicely many years ago, many is whatever, 20, he says there is a dynamic process of remodeling, and we can benefit from this dynamic process of remodeling. And this dynamic process of remodeling basically means that the brain who starts sleeping, being inactive, starts to be active, starts to be exercised. And it can be exercised because we provide altered inputs to motor controls, we provide an adaptation, and as a consequence, there might be that there is tools. So this changed cortical excitability leads to cortical plasticity. The cortical plasticity leads to better use of whatever we have. And if there are resources to be used, we can actually have and regain some function. So, among other techniques, which are intensive task-related exercise, constraint-induced movement therapy introduced by Tao many years ago, virtual reality being very popular, and we heard excellent presentation by Ander today, where this was really nicely exposed. But we go here to robot-assisted therapy and potential electrical stimulation. And here I am the topic. So there are two methods, basically, how you can control when you're talking of walking exoskeleton. There is one type of exoskeletons which are fixed machines, like an advanced gait trainer or a Logomat or a similar machine, Lopez, for example. They are shown here on an image. So what these machines, what they provide? They provide movement to paralyzed extremities. So they move the legs in a specific way. Since movement of the leg requires also other things like balance, there is a body support, body weight support, which comes from a suspensory system, which can reduce the weight to zero. So this is walking in air, or does not reduce the weight at all, so they're walking with a full power support. So with these devices, what actually happens is the following. You may have an individual, which is shown here, and this is a film that I got from Hesse, a colleague and friend of ours, who was developing one of the devices, and he's showing a typical therapeutic session of teaching someone to walk. And this is hard to say that this person is walking, he's more carried around by the therapist. So instead of having this person carrying a person, so what you can use a device, the one that was developed in Berlin, which was called Advanced Gait Trainer, and there are several versions of that now on the market. What this device does, it moves feet. And it moves feet more or less like the feet would move when someone is walking. There is a suspension system, and this treatment goes for about 2 weeks, and this is the same patient 2 weeks later. Obviously, on all movies, this is not the movie that I made, but if I made it, I would do the same. I would select the best patients who improve the best. There are some other patients who will be also crawling like he was doing. So, and if you look into the results of studies that are published, and meta-analysis that are published in Cochrane, you will see that there is no significant improvement in function if you use Advanced Gait Trainer compared to other things. If you look into some data, you can see that there is a modification in the gait pattern, there's a modification in the EMG activities, and I wouldn't go into any detail here, just to say that the training per se is changing the motor organization. So the training of locomotion of individuals with paralysis is changing the motor organization. That means that a different set of signals are coming to the brain. This different set of signals coming to the brain is generating a different sequence coming from the brain, and we have a difference in this. Probably the best known device and mostly used in the world, which has a price which is somewhere between 250 and 600,000 euro, depending on the version that you have, which is sold in many places, was developed by Hokoma in Switzerland. Now, this is all probably different organized in the world where the money plays a major role, like Ander said also. So this device does the following. It provides movement of legs, and this movement of legs is a replica of near normal movement. The device robot controls the hip movement and knee movement. There's only a spring which holds the foot, not so you don't have a drop foot. There is a specific mechanism which controls that the hips are moving up and down, left and right, more or less like they would do normally. And obviously this supports partly the body weight. There are various versions of this where you have a feedback, so there is a screen in front of you. There is a set of headphones that you have so that you are enjoying better in this exercise. There is a fair mounting. And the results of the Logomat are very much like of every other device like that. So there is improvement of functioning in incomplete lesions. This improvement is not significant in the sense that if you look into statistical analysis, the improvement compared to other techniques is not really up. But significant means a lot for statistics, but not for patients. There are quite a few of individuals who regain walking after being exposed to Logomat or Advanced Gait Trainer or other. Since the intervention is not too expensive, I'm definitely advocating that use of these training devices is very important So if we have 5% of individuals who can be improved, this is a lot. So if 5 people out of 100 can get walking and they didn't have it before, I think that's excellent. So the significance means a lot if you want to publish paper, but not necessarily if you want to help some individual to walk. The different version from these walking machines is an exoskeleton which is wearable. A wearable exoskeleton means that there is no other machine which is holding this. And there are many, and we saw actually a different image than I'm showing here. So basically what the wearable exoskeleton is a parallel skeleton to our skeleton. Making a complete replica that will be outside of the body is impossible. Duplicating biological joints is impossible. The fixing of these mechanisms of the body is another problem. Maybe we can use a technique that Dr. Mitković and Professor Mitković is using. So we use screws, and we go to that. Then we have a good fixation. Other than that, we don't have a very good fixation, and there is always a relative movement of a device or a system. These systems in general are relatively heavy. Many of them are 25, 30 kilograms. They have large batteries, and we are constantly developing many things. So, but nevertheless, these devices, they're great improvements, and I will show you from where some of these improvements are coming. I specifically picked up this video, which is coming from the Mihailo Pupin Institute. So this movie that you can see, you can read there, is made in 1972, which is 46 years ago. That's a standing frame, which is an exoskeleton for paraplegic patients. And this is an actually first made and first ever used exoskeleton for paraplegic individuals, designed by the group of Popović, and used in various versions with pneumatic actuators, hydraulic actuators, electrical actuators. What you do not see are cables, which are connecting to the power source and to the big computer mainframe, which was sitting on the wall. But as you can see here, there was a patient walking, and this was not the only patient walking. There was a group of patients. Mostly, these patients were flaccid with a lesion which was at T12 or L levels, so it was much easier to do. There were major problems in applying that if patients were spastic, because this triggered spasms, and these spasms were so strong that you can even injure some patients. So, in general, the device and the method is there. One of the beauties of the work of Popović is his invention of a zero moment point, or his expression of a zero moment point, which is used in basically every single device that is used. So he did an excellent contribution to the field, which is used everywhere. So the problem, one of the problems is the one that I already mentioned, that's the interface between a human and an exoskeleton. So the idea was born to have a soft exoskeleton. This idea that we have a soft exoskeleton was first tried in France, in Toulouse, in Montpellier, by Pierre Rabichon and a couple other people. Our group, not my group, Professor group from Professor Popović participated in that, and you can see there at the top in the left corner right here, that's the Aerosure. That was the first system where you have a soft interface. Aerosure is an anti-gravity suit which was used. You blow up the tubes, you have a fixed structure and a person can stand. The only problem is he wants to sit, you have to unblow that. So you need a compressor, other than that you're okay. The other problem was that actually there was no skin breathing with this. That was one pressure, and the pressures that were applied to the body were relatively high. So they went a step further, and they made a modular system, which the project was called AMOL. This project was finalized in 1978. And what you see in the right image there, that's a system with son of Pierre Rabichon, Emmanuel Rabichon, was working. So there were 2 exoskeletons, one weared by the therapist, one weared by the patient. So whatever the therapist does, master-slave controls implements on the patient. So this was used for some time. Actually, this was the time when I also started my research, and I built and designed an orthosis which we'll call self-fitting modular orthosis, which was a soft orthosis. And what is interesting with this led to different projects, but I have to show, just for fun, that's the patient in 1987. This patient in 1987 is using a combination of electrical stimulation and self-fitting modular orthosis. This is a complete lesion, T11 patient, who, as you can see, can walk, and that is not too bad. Walking is maybe a wrong word because that's more ambulation than walking, but certainly he can move, and he used that for almost 2 years. But we're talking about very motivated individuals who like to participate in exercise, who like to be exposed to people, not a regular device that can be used for better. So today, we made a step forward, and there are different devices. I will show the Rewalk, and Rewalk is an interesting system where you can see is an exoskeleton and a person can enter in. This is meant for individuals who have a reasonable balance, good control of upper part of the trunk, reasonable strength in their arms to maintain balance. And as you will see here in a second, so you see you have a stiff connection in ankle, so the ankle is not moving, and you have here now a power gate. Somewhat different devices which provide stability is the system that you see here, which is BioRex. So BioRex provides even more than that. It's a self-contained system which allows complete stability, meaning that this is basically a standing wheelchair. So when you enter into this machine, the machine is stable, and the machine will carry you and move you from one point to another point, even going some stairs and other activities. There is a simple joystick that you can use. There are pre-programmed strategies. As you can see here, the person can stand up with this, and when the person stands up, that's fine. So, but that's not the simplest system. It has to be completely adapted to the person. So all the measures needs to be made perfect in order that the machine fits to. Well, that's all doable in a way. So there is a major improvement. This major improvement can be seen. Last year, actually a year and a half ago, there was a competition, triathlon, competition of machines, not of individuals. So companies and different researchers were competing to show how their technology works. So there it was a competition on exoskeletons, artificial legs, artificial arms, wheelchairs, tricycles, and something else also, whatever. But here you can see how top of the line, one of the competitors is actually walking with a device like that. And you see that this is not really terrific and that it needs a lot of improvement to be made before this can actually make a step forward. Now, there's a long way, as I say here, with this. But the benefits, to be really honest with that, of using an exoskeleton are here. People who use exoskeletons, because they're vertical, because they're active, what happens is, in most cases, as an end result, they have a decreased plasticity, if this is applied appropriately. What happens is, because they're standing, because there's a different circulation, because there is a different body posture, different distribution, in them, what has been noticed is that there are reduced incidence of urinary tract infections. They maintain the joint range movements, their muscle contractures are not there, and they definitely have improved metabolic function, including cardiovascular system. With red, I have something which I want to point out. I think that exoskeletons, what they need to have, and then they will have a full implementation, this is that they have carry-over effects. I don't think that individuals are ready to be robots. I think that individuals want to be humans. And I disagree with this idea. So as long as they use a machine to assist me for some time, I wouldn't have a problem. But if I have a live friend, which is not really friendly, then I am developing slowly a life enemy. Most of systems that I've seen so far, definitely most of that I developed myself, they ended up collecting dust on some shelf. So they were used and they're interesting, but at the end of the day, they were not good enough. And good enough means that there was someone who is really willing to use that in a way. So there is an alternative, obviously, to exoskeletons, which is very popular. And what I used for the first time, I believe, so instead of using electrical stimulation, I intentionally wrote powered endoskeletons. So why we should bother with an exoskeleton if we already have a skeleton in the body? So why we don't try to drive the skeleton that we have in the body? And obviously there's a possibility how to do this, and this possibility is to activate muscles. So we do have actuators in our body, we do have a skeleton in the body, so why using any external parallel skeleton, parallel motors, parallel batteries if we have that already in the body? So this idea came many, many years ago, and we heard today it came with a pacemaker. I will actually make an addition to what Anders said. I think he said that. He said with a pacemaker started. You have this slide. But actually it started with an electrical chair. So the first device with electrical stimulation was the first electrical chair, which is for death penalty. It worked excellent, and it's still in use in some states in the United States. But you disagree?
No, not really a rehabilitation.
Not rehabilitation, but actually it is. It's social rehabilitation. It's not individual rehabilitation. So anyway, electrical stimulation is known for some time, from the time of Dejan, where he was having these phases. But what the group in Ljubljana and some other developed was a very simple system. And this very simple system is shown here. So this is one of their probably best patients. And as you can see here, the movie is from 1984. This was work of Professor Academician Alex Kralj that they buyed and many others who were participating in this. And Sándor, who is a guy from Austria, who liked that, he used it for several years, and he was able to cover long distances. So what he has here is a 4-channel electrical stimulation and a set of 2 switches, which is for left and right hand. So whenever he pressed the left hand, this will switch the swing phase. Whenever he pressed the right switch, he will turn the right leg swing. If he pressed 2, both in the same time, which means both leg swings, there is a safety mechanism which says, no, 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 no. You can't swing both legs because you're just walking, you're not jumping. So in general, this system was implemented. There's a nice book written by Kraljenbeit, which came in 1989. This describes about 112 cases. But after that, this work somehow stopped for various reasons, and we have only anecdotal data afterwards. Definitely, this can be improved, and I continued working in this domain, and this was the work which was happened at the Miami Project to Cure Paralysis in the early 90s. And I think that this is one of rare applications where we had a complete automatic control. So 12 individuals that were in the Miami Center participated in the study with the Parastep system. In parallel, we built up a complete automatic control, and we could have these individuals, and they're all young Cuban motivated people to regain standing and walking, and they were really looking for that. In all of them, we followed all kinds. There's a series of papers that were published from the group in Miami Project where they demonstrated that everything I showed, so this is cardiovascular system, metabolic functions, gastro functions, bowel functions, everything was improved. The only thing which did not improve, there was no carryover effect whatsoever. So as long as I use my stimulation that works, if I turn it off, there's no carryover. So they need to use stimulation. In order to set up a system like that, this is like 30 minutes. How long they can walk? 15 minutes. So who wants to put the system 30 minutes on in order to walk for 10 meters and then he needs a wheelchair? So the technology was not there. There was an effort in Cleveland by Marsley and others who built implantable systems, and this worked very well for some time, but really stopped. Another problem which you saw in all of those films and movies and images was that all and every individual, they actually carry with them crutches or walker or something else. And on the first part, you saw the systems which are carrying the weight. We built a very nice and interesting system which is called Walk Around, which is partly following ideas and that I gained from Zlatko Matjačić, who will be talking a little later. And this is actually that instead of having this type of support, you provide support which will give the orientation to the trunk. So the system that we built actually has a belt, and this belt provides orientation to the trunk. So it gives the stability, it doesn't allow the person to collapse. So if something works bad with our exoskeleton or our electrical stimulation, this can work. The advantage of our powered walk around, which is controlled by joystick, either by patient or by therapist, is that you can walk everywhere and you can have long sessions, and you're actually walking on the ground. That's not a treadmill, so it might be motivating and you can cover distances. And we had this in long application. So this is, again, a therapeutic device. No one is going to use a device like that as a friend. But a lot of people will use a device that as a therapy if they know that something will be in. So since I covered some of the aspects on lower extremities, I'll just go to upper extremities. For upper extremities, there is a series of various devices that are on the market. One where the thing started mostly was definitely one that comes from MIT, works from Krebs as one of the leaders of the group, but starting actually with Hogan. Isn't it interesting? What they built a machine which had 2 degrees of freedom, and was a robot which can assist movement, or they can record movement and provides to a person ability to exercise and move the hand. Excellent clinical studies demonstrated that if you use the device in about 8 weeks, you regain manipulation and control of upper extremities, you stop using that, and in 6 weeks, you're back where you started. So the machine was assisting, machine was good, but since the improvement in overall function is not good enough that you continue to use your arm, you go back to no-use pattern, and because you go back to no-use pattern, this doesn't work. A very nice robot assistant is definitely one that you can see here, and the Haptic Master, which was developed by Moog, now it belongs to the company Motec, which is Netherlands again. It's a very nice and simple gimbal, and this gimbal provides the position and the orientation of the forearm, so a person can do excellent exercises. This machine was used in many studies, in many European projects, and it provides an excellent training source for individuals who do not have control over their. Yeah. It is linked to a set of video games, so you can play different games and you can do various things in a nice and effective way, so in order to do and control things in a wide and good way. A different approach, where you control not only one point on the arm, but you actually control several points, is an exoskeleton. And most likely, at least to my eyes, the best development was done by the Hokoma company in Switzerland, where they built various versions of RM. That's not the only version, that's probably not the best version. There's some very nice development, Delft and in Twente, maybe even better than that, but Hokoma came the furthest. So what you can see here, the robot can provide various functions, including wrist position, elbow position, arm position, so you can actually exercise. The machine can be in a passive regime, so the person does everything he can. It can be the semi-active, where the device detects what the person can do, or it can be just a device which drives the hand through a range of motion. That has great advantages, and at one time we actually had a project with the ETH Zurich where we wanted to combine this device with electrical stimulation to control the hand. And going into this direction, adding hand functions by electrical stimulation would make really a difference. This device per se still did not really show what it is. What this electrical stimulation of hand is. I showed this very nice movie designed by the company Technalia. I don't know, maybe you know the company. So this is a device which was partly developed in Belgrade and by our team. And what it has a set of array electrodes. These are array electrodes. They are actually activating the muscles selectively in a distributed way. So you can program this all through a nice wireless communication, and the person can open the hand and close the hand. This system does not provide control of manipulation. So if a person does not and cannot manipulate with the arm, it's useless. He can exercise the hand. But since most people, they do have some function of manipulation, they start with. So this device is specifically used for exercise of function, and it has reasonably good results. Speaking on upper extremities, definitely the best ever developed system is a system developed by the company which is in Cleveland, and they ended up with a freehand system. The work is abandoned, the company is bankrupt, but Hunter Peckham, who is behind that, he's investing his personal money to get the device to work freely. So freehand system is the best upper extremity electrical stimulation which is completely implanted. So stimulator is implanted, recording electrodes are implanted, stimulation electrodes are implanted, and everything works. With a somewhat different version, which was original, there's probably 400 individuals in the world that are using this, tetraplegics. This device is not meant for therapy. It is strictly made to provide tetraplegics with the functions so that they can have an independent life. And that's the beauty of the implant. Once they have the implant, they can manipulate. There's nothing to do, so you turn on the device and you're active. Therapeutic effects have been demonstrated, and some of the best patients in Cleveland, they actually improved so much that they can do a lot even without the stimulator on. So they're Jim Jerich, the best patient. When he implanted a system for raising the hand above the hand after 6 months, he was doing the best when he turns the system off. So there are some therapeutic effects, but in general, these effects are neglectable. We built here a system that was used for therapy, and I think that's a nice addition to everything else, which needs to be combined with some of exoskeleton for manipulation. This system controls completely the grasp. That's a system which has a full adaptation of opening and closing. That device was brought and has a certification to be used in clinical research. And there are nice paper and studies that were done with that include more than, I would say, 300 individuals in several research centers. But again, this is all limited, and we are still not at the point where we can do good things. So just before I conclude, I want to say that if a device, exoskeleton and the skeleton control, is applied timely, so soon after the injury, it will increase the abilities of a person to do very much. This will be a major motivation for exercise. If this achievement is good enough that this person regains function, there is a very likely chance that the person can use that and maintain this function that she or he gained. So having exoskeletons, the therapeutic devices which are assisting people in a good phase are definitely a good thing. In a summary, we will have to try to demonstrate these devices are assistants to rehabilitations. So what they are doing, they are replacing partly therapists, they are assisting therapists, They're implementing biological strategies, and they are definitely something that can make a difference. If they are selected appropriately, very likely what Marco Molinari said, if they are used timely. If they are controlled also, in addition to this, with some brain signals, very much like Andre was proposing, then we are making a good situation, and we're coming to this, get a smile back to the patient face. And that's the idea. And that's what I wanted to say. Thanks.